Hello, welcome to Lecture 9 from Math 155. Today I'm going to be talking about a review of the derivative, which you learnt about in Math 154. So the reason we are talking about derivatives again is because we've just talked about functions of multiple variables. Previously, you learned about derivatives of functions with one variable. We're going to be talking in the next lecture about how we take derivatives when we have functions with multiple variables. So the purpose of this is just to get you thinking about derivatives again, make sure you can remember what the definition of a derivative is, how we visualize it, how we compute it, and so on. So have a read of this outline slide. We're going to be coming back to this example of blood alcohol concentration with this figure up in the top right at the end. Okay, so the definition of a derivative, well, its formal definition is if we have a function f, then the derivative of f at x, some value x, f prime of x, is the function f prime of x is equal to limit as h tends to 0 of f of x plus h minus f of x divided by h, if this limit exists. Okay, so this doesn't always exist depending on the function. If it doesn't, then the function, we can't find the derivative of that function at a particular value. If it does exist, then this is how we compute it. So this is its formal definition. We can write it as f prime of x. We could also write it in various other ways. For example, dx here of f of x, or df dx, or dy dx if y is our output variable. And we say that at a particular value a, x is equal to a, our derivative is just, we sub in that a to our f prime, so we get f prime of a, or we can say df dx evaluated at, so this vertical bar here just means evaluated at x equals a, so evaluated at, and then x equals a. So when we find the derivative at a particular point x equals a for our function f of x, what we're really doing is we're finding the tangent to the curve y is equal to f of x at the point a, f of a. So if we draw the line curve y is equal to f of x, and then we look at the point a, f of a, which is the point on that curve, then the line, the straight line going through a, f of a, which has slope f prime of a, has the equation y is equal to f of a plus f prime of a times by x minus a, and that line is the tangent line. Okay, so just to illustrate what's going on there, here we've got a quadratic curve, and we want to find the equation of the tangent line to y is equal to x squared minus 3x at x is equal to 2. Okay, so where this red dot is. Okay, so the first thing we want to do is say, okay, well, we've got our function f of x is equal to x squared minus 3x. So if we calculate the derivative, we'll talk about how we can calculate this in a couple of slides' time. We use the power law here, so these are the powers of x, so we can just bring the 2 to the front, reduce the power by 1, so we have 2x here from the x squared, and then minus 3 comes from the derivative of 3x. And then if we want to find the equation of the tangent line at x is equal to 2, then we need to substitute in 2 here. So when we do that, we get 2 times by 2 minus 3, which is just equal to 1. So the slope of our tangent line at x equals 2 to this curve is 1. So if we draw this on, I can hopefully draw it on reasonably well. Our tangent line looks something like this, approximately. This is the line that is tangent to the curve at x is equal to 2. And this has slope 1. So slope 1. And we can write down the equation of that tangent line as follows. So our tangent line, well, this is the line y is equal to, we go back up here to this equation here, so f of a, so f of 2 here, because our a is equal to 2. We're assuming if we're doing x is equal to a and a is equal to 2, then we put in 2 here, so we have f of 2. Then we need to add on f prime of a times by x minus a. So we need to add on f prime of 2 times by x minus 2. Okay, so we work out what this is. F of 2 is equal to minus 2. And we're going to have to f prime of 2, well, we know that the slope of our tangent line is going to be 1, so just put the 1 in there, and then x minus 2. So the equation of this is going to be y is equal to x minus 4. So this is the equation of our tangent line, this line here. Okay, so that's the equation of our tangent line. If we've got a function that we can take the derivative of, that's all well and good. Sometimes we just have data to work with. For example, here we've got these different data points, and we want to say, okay, approximately what is the gradient? Because the gradient at a particular point was the derivative at a particular point tells us what the gradient is, and that gradient tells us the rate of change or something at that point. Okay, so that's all it's telling us, is saying, okay, well, how much are we changing by approximately at that point? So we can work this out in this particular example by saying, okay, well, here we want to work out what is the approximate value of the gradient at when t is equal to 8. Okay, so when the time point is equal to 8, unfortunately there's two t's here. When lowercase t corresponds to time and capital T corresponds to the temperature in Fahrenheit. So you want to work out what is the approximate rate of change at this time point. Okay, so this is this time point here. So how can we do that in this case? Well, we can go back to our formal definition up here, and we can use this as an approximate. So rather than taking the limit, we can just say, okay, approximately what is this gradient going to be by using a point close to this point when t is equal to 8. Okay, so at this time point here, well, we can say, well, we've got a close by time point. We can look at this time point up to the next step. So when t is equal to 10, we say, okay, well, actually, let's do it in a different color. We want to find the gradient of this line. So although these dots are joined up, the things on the line don't actually exist. Okay, so those points aren't measurements. So all that's happened here is the dots have been joined up. What we want to do is we want to say, okay, well, approximately what is the gradient here? Now we could use a point that's further away. For example, we could say, well, we could use this as an approximation by looking at the gradient by comparing these 2 points here. But obviously that's going to be a worse comparison because those 2 points are further away from each other. So we want to work out what's the difference here. Well, okay, so the differences in the x values here along the x-axis is going to be 10 minus 8. And then in the y direction, it's going to be t of 10 minus t of 8. Okay, so we can therefore say that t prime of 8 is just going to be approximately equal to the difference in the y's, so t10 minus t8, over the difference in the x's, so 10 minus 8. So if we substitute in those values, well, we've got these values here. So on the top, we're going to have 57 minus 51. On the bottom, we're going to have 2. So that's just going to be 6 divided by 2, or 3 degrees Fahrenheit per hour. So this is saying at 8 o'clock, the rate at which temperature is increasing, because this is positive, is 3 degrees Fahrenheit per hour. Okay, so if things were to continue linearly at that going on in the future, then we'd expect at 9 o'clock the temperature would be approximately whatever it was at 8 o'clock plus 3 degrees Fahrenheit, and then carry on to 10 o'clock, another 3 degrees Fahrenheit, 11 o'clock, and so on. Obviously, as the further and further you go away from that measurement, the approximation that we've made, the less likely it is that your approximation is going to be valid. Okay, so this kind of approximation works well when those points are close together. But as you go further and further away, they're likely to be quite different. Okay, so how do we calculate derivatives? There's a whole host of different rules that you should remind yourself of. Hopefully you covered all of these in Math 154. So for example, if we try and take the derivative of a constant, we just get 0. If we have something of the form x to the n, that's a power rule. So we just move the power to the front and then subtract 1 from that power. So we have nx to the n minus 1. The product rule, if we've got two functions, f of x and g of x, we multiply them together and we want to take the derivative of that. Well, we take the sum of the first function, f of x, take the derivative of that, as we have f prime of x times by g of x, and add that to the other way around. So then we have f of x times by g prime of x. The quotient rule is a little bit more complicated, assuming that g of x is not equal to 0. In this case, we do almost the same as what we did with the product rule, but rather than adding them together, we subtract them. So this is a minus here, whereas it was a plus here. And then we divide everything through by g of x squared. Note that that's g of x squared and not g prime of x squared. Okay, so just remember that you're not having g prime of x here on the bottom. And then the chain rule, if we've got a function of a function, so if g of x is our inner function and f of g of x is our outer function, then we take the derivative of our outer function f here, so we have f prime evaluated at g of x, and then multiply that by the derivative of g, so g prime of x. There are also various other basic functions that we should remember. If you have e to the x, the derivative of that is just e to the x, and that's the special property of the exponential function. We also have these other ones here, which I won't go through now, but just remind yourself of these. Okay, so if we think of an example, if we have f of x is equal to e to the x squared, well, let's think about what this actually means here. This is a composition of two functions. Okay, so this is a composition of, let's call it g of t is equal to e to the t, and h of x is equal to x squared. I just changed it to a t here just to illustrate that it's something different so we don't get our x's confused. And then we have f of x is equal to g of h of x. So g in this case is our outer function and h is our inner function, and that's our e to the x squared. Okay, so the t here is just a dummy variable that we're using. Okay, so if we think about what g prime of t is, it's just going to be e to the t. And so if we think about f prime of x, well, we're going to use the chain rule here. So remember the chain rule, this one here, we want to take the derivative of the outer function, which in this case is our g of t, and then evaluate that at t is equal to h of x. Okay, so that's the first part. So we do f prime of x is going to be equal to, I'll leave this here actually, just so we can see the chain rule as well. So we're going to take our g prime of t, so that's just e to the t again, and then evaluate it when t is equal to the inner part, so that's h of x, which is x squared. So we're just going to have an e to the x squared here. So just to make sure that's clear, you take the derivative of your outer function, which is this, in this case, just happens to be exactly the same as what we had before. And then we evaluate that at whatever our inner function was, which is setting t is equal to x squared here. Okay, so that gives us an e to the x squared, and then we're timesing that, multiplying that by the derivative of our function that we had on the inside, which in this case was h of x, which was x squared, so the derivative of x squared. And then just to make sure this is clear, this is by the chain rule. Okay, so if we take the derivative of x squared, then we're going to get 2x, thinking of the power rule here. So we can write that out at the front, 2x e to the x squared is our answer. Okay, the next example, if we've got g of x is equal to the square root of x, we can think the square root of x is just x to the half. So this is just a power relationship as well. So we're going to use the power rule on this. Divided by 1 plus e to the x squared. So e to the x all squared. So 1 plus e to the x all squared on the bottom. So this is going to be a composition here. So let's write this all out. So g prime of x, first of all, we're going to want to use the quotient rule. So this means, if we go back up here, what did the quotient rule say? Well, we take whatever was on the top, our f of x, and we take the derivative of that and multiply it by what we had in the denominator. And then we subtract whatever we had in the numerator and multiply that by the derivative of what we had on the denominator. So let's do that first. So here we're going to have half of x to the minus a half. Where did that come from? Well, this is the derivative of what we had in the numerator, derivative of square root of x, which is equal to x to the half. So we take the power to the front and subtract 1 from the power. So we have that multiplied by whatever we had on the bottom, so 1 plus e to the x squared. And then we're going to subtract whatever we had on the top. So I'll just write this as root x here because it's slightly less messy, multiplied by the derivative of what we had on the bottom. So the derivative of what we had on the bottom, okay, that's going to be a little bit complicated again. So again, I'm just doing this bit here now. F of x times by g prime of x. So I've got our f of x, which is square root of x, and the g prime of x here. Unfortunately, because of there's a g here, so you can think of this, it really would have been better to give this a different letter. I'll tell you what, to avoid confusion, I'm just going to change this to an h of x. This is h prime of x. And then this, the bit on the top, the square root of x is f of x, and the bit on the bottom is our g of x now. So g of x is equal to 1 plus e to the x all squared. So call that g of x and this bit f of x. Hopefully that will make things a little bit clearer if you're going back and comparing it to the rules above. Okay, so we need to take the derivative of g of x here. This is a composite function itself. Okay, so we first of all need to do basically what we did above in the first example and apply it to this example here. So we have 1 plus e to the x all squared. So we can think of our outer function as being t squared. So we take the derivative of that and we end up with 2t, and we evaluate that t at whatever our inner function was. So we have 2 times whatever the inner function was, so that's 2 times by 1 plus e to the x. And we lower the power by 1, so we have had 1 there. And then we multiply that by the derivative of whatever we had on the inside of our function, on our inner function, okay? So in this case, that's going to be the derivative of 1 plus e to the x, which is just going to be e to the x. So here, just kind of e to the x. And then this is all over whatever was on the denominator, in this case, g of x all squared. So g of x all squared is just going to be 1 plus e to the x to the power of 4. Okay, so this is kind of messy. We can do a bit of simplification here. We can divide through, note that we've got a 1 plus e to the x here, and we can get rid of one of them there and one of them here, so that goes down to a 3 now. So that's made things a little bit simpler. We're going to have a 1 over 2 square root of x over here, and we're going to have a square root of x here. That's a little bit messy. What we can do is we can take out a factor of 1 over square root of x and put that on the bottom. In fact, we can do 2 over square root of x. In that case, actually, I'll leave that step until just afterwards. Let's keep things fairly simple at this stage. So let's write this as 1 over 2 root x times by 1 plus e to the x minus 2 root x e to the x over 1 plus e to the x to the 3. Okay, so I haven't done anything additional there except for writing the square root of x's. So like I said, we can take out this factor here of 1 over 2 root x and put that on the bottom, which means we need to multiply this term here by 2 root x in order to make things balanced. So when we do that, we're now going to have 1 plus e to the x here minus, well, we're going to multiply this second term here, this 2 root x by 2 root x, so that's going to give me 4x. And then we've got our e to the x divided by, well, we've pulled out this 2 root x, so that 2 root x goes on the bottom here now. And we're going to have 1 plus e to the x cubed. Okay, so those examples were quite messy, but go back and try these yourselves without looking at these answers and see if you get the same result. You can also just come up with functions yourself and work out what the derivatives are by, you make sure you're familiar with how to use the chain rule and the quotient rule, and so on. And to check your answers, you can just plug them into Wolfram Alpha and see if you get the right result. Okay, so we've worked out how we can calculate the derivative in different circumstances, but what is a derivative? Okay, Okay, so if you think about it, if you have a function, you take some input, you do something to it, and you get some output, what the derivative is telling us is if we change the input by a certain amount, how much do we expect the output to change by approximately? Okay, so this is an approximation. And it's saying that, okay, if we zoom in enough on anything that's nonlinear, anything that's like nice and curved, if we zoom in on that enough, then it looks approximately linear. So if we're close to it and we change the input by a bit, we should roughly get that our function should approximately be roughly what our output is given by our tangent line close to that point. Okay, so if we, for example, have a function f, and we don't know what this function looks like, for which we know that f of 3 is equal to 2 and f prime of 3 is equal to minus 0.4, what can we say about the values of f that are fairly close to it? So f of 3.2 and f of 2.5. Okay, so if we draw some function, okay, so we know that at the point when x is equal to 3 and y is equal to 2, that our function passes through this point. Okay, but we don't know anything about what that function looks like. Okay, so for all we know, it could do some crazy thing like this and carries on doing whatever. Okay, all we know is that at x is equal to 3, that our tangent is minus 0.4. So our tangent at that point looks something like this. So this here has slope minus 0.4. So we can use this gradient, this tangent line, to approximate values nearby. So we know what the value of f is at 3. We don't know what the function f is, but we can say, okay, what's the value at 3.2? It's nearby. So we can say that f of 3.2 is approximately equal to what we had before at f of 3. And then we're going to move along our tangent line. So we say, what's the gradient at f of 3 and the difference between the point we're interested in, 3.2, and the point where we're getting our tangent line from, so 3. So this is just then equal to 2 plus minus 0.4 times by 0.2, which is equal to 1.92. So this point here is approximately equal to 1.92, or rather that is the exact point on the tangent, but the point of the function is going to be approximately equal to 1.92. Similarly, we can do the same for when f is equal to, so when x is equal to 2.5, this is going to be approximately equal to what we had when x was equal to 3, and then moving along the tangent line from 3 to 2.5, so 2.5 minus 3 here. So here, this is just going to work out to be 2.2. So this value, 2.5 up here, is going to be approximately equal to 2.2. This is 2.5. So our derivative is telling us something about, if we're relatively close to a point that we know about, what is our function approximately near there. Okay, so I mentioned at the beginning that we had this example of blood alcohol concentration. So this is just these data that are shown in that table there are plotted on this graph here. So I'll just talk about it here for a second. So the orange line is showing our derivative, and the blue line is our actual blood alcohol concentration here. So this is the actual, and this is the derivative at each of these different points. So how do we work out that derivative? Well, if we've got all these different data points, we can apply the same logic that we just did on the previous slide. So if we have a value of C of t, well, we can say what is approximately the gradient at that value. So if t is equal to 0, for example, we have C of t is equal to 0. Well, what's the gradient at that point though? Well, we look at the next closest point, 0.25, which occurs at t is equal to 0.2. So in this case, C prime of t is going to be 0.25, so the value of the next value along, minus the current value, 0, divided by the difference in time, so 0.2 minus 0, which is just going to be 1.25. So our gradient at 0 is 1.25. So if we go all the way back to the beginning to that figure, this up here is approximately 1.25. Okay, we can carry on the exact same process. If we go to the next one, for example, I'll do this now in blue. So now we're going to shift everything along one. So our point here, we're going to be interested in 0.41 minus 0.25. So what's the value at the next time point minus the current one? And the difference in time, well, here the time step has changed now, so it's no longer 0.2. It's going to be 0.5 minus 0.2, which is 0.3. So 0.5 minus 0.2. So that's 0.16 over 0.3, which is approximately 0.53. So you can keep doing the same process. It's kind of laborious to be working this out by hand. Have a go at doing this yourself. You can also plug this into a computer or a spreadsheet, and you can work out exactly what those values are. And you can just apply the same formula here, which is based on the original definition of the derivative, but without the limits. Okay, so you take whatever the next time point is, you subtract the current time point, and then you, on the denominator, you have the length of time. Okay, that's it for our review of the derivative. Make sure that you have remembered how to calculate the derivative, what its definition is. We're going to be moving on soon to talking about partial derivatives. So when we've got functions of more than one variable, how do we work out derivatives in those situations? Okay, thanks very much. Bye.